All right, we are going to wrap up this unit by starting off by looking at some kind of the exceptions I noted at the beginning of the discussion of REO or determining acid strength. And then we'll look at some kind of interesting things that happen within acid-base chemistry of organic chem. So one of the first exceptions I want to take a look at is an interesting case that comes up with sp3 hybridized carbons. So remember, I had pointed out quite a bit that hydrogens and sp3 carbons are never acidic. The pK is just way too high. Their bases don't exist to deprotonate as those hydrogens on sp3 carbons. But there is one notable exception. And we're actually going to spend a lot of time on this exception, I believe, next semester. And that's when there are hydrogens on sp3 carbons next to carbonyl groups. We call those alpha hydrogens because they're on an alpha carbon. And alpha just meaning it's the first carbon outside of that carbonyl, that carbon-oxygen double bond. Now, for comparison, the hydrogen on, not an alpha carbon, just a regular sp3 hybridized um, carbon, the pK is 51. So again, impossible to deprotonate. But put that next to a carbonyl, and now we're getting to something that's it's still fairly weak, but it's much more acidic than it was before. And so let's imagine a base deprotonating that hydrogen. And I want you to take a look at this anion. I want you to think about why the acidity now increases. Why does that pKa go down? Because and it must have to deal with that carbonyl. So again, think back to the whole REO discussion. The whole goal behind that was to see, is there anything that makes an anion more stable? So if I compare that to this over here, and again, let's just say, you know, magically somehow there is a base that can deprotonate that. Compare those two ions. What's the main difference? This one over here can undergo resonance. And what do we call that? When we're able to spread a charge to multiple atoms through resonance. That's resonance stabilization. The one over here can't do any resonance. That ion's not stable, and putting a negative charge on a carbon is a very, very, very unstable charge. Not that you won't ever see it, but for an sp3 carbon, it is very unstable. So let's do a few practice problems. And just to kind of solidify some of the things that we have talked about. And I'm going to also highlight some more, I should say, exceptions that you're going to see periodically in which REO doesn't really help out, or we don't see that order of priority that we normally do. Okay, so in these first couple of questions here, they're basically asking us, will water protonate this anion? So in order to really figure this out, we're just going to get the full practice, and let's draw the acid-base reaction of water protonating this ion. And I'm going to draw in the lone pairs of that nitrogen. Now, how do I know it has two lone pairs? It's got a negative charge. And we're going to react that with water. I'm going to draw water like this because we're going to get practice doing the mechanism. So water is going to be our acid. So we draw a proper curved arrow showing the base pulling off a hydrogen from the acid. And then we move these electrons between the hydrogen and oxygen back to the oxygen. And so now that nitrogen is protonated, no longer has a negative charge. And then we have hydroxide over here. Now this is our conjugate acid, and this is our conjugate base. So what we're going to look at is the stability of the bases and ask ourselves which one is more stable. So compare the negative charges. So we got a negative charge over here and over here. Now we're going to use ARIO and start with atom. The atoms are different, so we can use that part of ARIO. On the left is nitrogen, on the right is oxygen. So remember, since they're in the same row, we're going to use electronegativity. Oxygen is more electronegative, so it can handle a charge better than nitrogen can. So this is more stable, and the more stable ion comes from the stronger acid. And kind of remember the golden rule of acid-base equilibrium. Equilibrium lies away from the stronger acid. So this equilibrium favors the product side, which means we can use water to protonate that N minus. Now let's take a look at D. So again, let's set up a reaction, practice drawing a mechanism. And there's our anion. So what happened was maybe that hydrogen in the middle got deprotonated. And then we're going to see if water is sufficient enough to deprotonate it. I'm sorry, I'm going back up. Water is sufficient to protonate it. So actually, let me fix that. We're going to start at electrons. Draw our two arrows for our acid-base reaction. And then again, we're making hydroxide on the right. This is our conjugate acid, conjugate base. Now, in order, again, to determine what direction the equilibrium lies in, we need to figure out what is the more stable base. So over on the left, the atom with the charge is carbon, the atom with a negative charge, and on the right, it's oxygen. So again, those two things are in the same row, so we base it off electronegativity. So we would think that, all right, this should be the more stable base. Okay, so that's the more stable base. And that should come from the stronger acid. But here is one of the exceptions I wanted to point out. If we look at the pKa values for our acids, the pKa for this, what we call a dicarbonyl, is between 9 to 11. Somewhere between there. The pKa for water is 14. Now, this is one of those cases where if we use ARIO and we stop at the atom like we normally would, we'd actually get to a wrong answer. Here, resonance plays a much bigger role because I can draw a lot of resonance forms for that base. So according to the pKa, this acid on the right, the conjugate acid, is actually stronger. And water is a weaker acid based on the pKa's. And so this equilibrium favors the reactant side. So to fully answer the question, we would say, no, we can't use water to protonate this base because it's a reactant favored equilibrium. So this is just one of those weird exceptions to know. So a weird exception. And generally, if this were to show up on an exam, I would kind of tell you, well, there's an exception to this equilibrium. Here are the pKa values. Can you try to explain why this exception might exist? And for this one, it has to deal with there's a lot of resonance for that anion, that carbon anion. And that kind of, in this case, outweighs the fact that the atoms are different. Now, a similar sort of exception to know, and we're going to see this quite a bit in a couple of chapters, is when we use a really strong base like NH2 minus to deprotonate something called a terminal alkyne. Now, what that means is that in a carbon chain, if there's a carbon-carbon triple bond, it's at the end of the carbon chain. When it's at the end, it's got an extra hydrogen at the end. The carbon, when it's at the end of the chain, this carbon has a hydrogen on it. Now, if I draw the results of this acid-base transfer, we'll see we'll get these products. Now, if I were to go off of Ario says I look at atoms first. Ario would basically say, well, this base is more stable than this conjugate base because it's the atom. But if I were to look at the real numbers, the pKa for this terminal alkyne is much lower than the pKa of the acid on this side. So this is a product-favored equilibrium, even though Ario says I should look at atoms and then stop. In this case, I'm just kind of skipping all the way to the end and looking at the orbital. Having the negative charge be on an sp hybridized atom is much better than having it be on an sp3 hybridized atom. And as I said, this is kind of a unique exception, but we're going to see it quite a bit in a couple of chapters. All right, now another thing you should be able to do is that if a compound has multiple possible acidic hydrogens, you should be able to identify which one is the most acidic. So let's look at A, and we're going to compare red to blue. So let's imagine deprotonating both of them. So we're going to use a base, and we'll go down the red pathway here and deprotonate the oxygen. And let's compare that to the blue pathway. And what would that look like if I were to deprotonate the blue hydrogen? So now we're going to just compare them. All right, start with Ario. A in Ario stands for atom. Look at the atom that has the charge. So in this case, we have oxygen on the red, carbon on the blue. There's a big difference in electronegativity. And so we would say the red one is more acidic. Now let's look at B. So if I were to deprotonate the red hydrogen, I would get this. as the anion. If I were to deprotonate the blue, I would get this as the anion. Now, if I start with A and Ario, I don't see a difference. They're both on carbons. So then I go to R. R stands for resonance. Is there certain resonance or more resonance stabilization in one versus the other? Well, let's just draw some resonance forms and see. So I'm going to draw a resonance form starting with this one. I'll move the electrons here like this. And that's good because I put the charge on another oxygen, or on another atom, I should say. Can I do anything else? Because I can do that on the blue one. I can do this for the blue one. That one has resonance as well. So is there any difference? Well, let's go back to the red one. I can do this. Move this here to make a double bond. Move that pi bond over there and move this up. And now the charge is on a third atom. I can't do that on the blue pathway. There's nowhere else that negative charge can go. So there's more resonance stabilization on the red pathway, meaning the red hydrogen is more acidic than the blue hydrogen. And then finally, let's look at C. So let's imagine deprotonating the red hydrogen. So I get this ion if I deprotonate the red one. If I deprotonate the blue one on the nitrogen, I get this one. Now again, we're going to start with Ario, start with the A. So the atom on the red, or the atom with the charge in the red pathway is an oxygen. The atom with the charge on the blue pathway is a nitrogen. And already we can see there's a difference in the atom. So look at our periodic table. Oxygen and nitrogen are in the same row. So we're going to base it off of electronegativity. Oxygen is more electronegative than nitrogen. And so that's where we're going to stop there. The red hydrogen is more acidic than the blue one. Yes, both of them can do resonance. I encourage you to practice this. Both of them, you can show resonance moving the charge to another atom. So maybe try that. Get some practice with resonance. You're going to have to do it on your test. But according to Ario, this is not an exception. I'm just going to, kind of tell you, this is not one of our weird exceptions that red hydrogen is more acidic because of the difference in atoms. Now, we haven't really talked much about bases, but bases are pretty much kind of like the opposite of acids. I've highlighted one of the most important trends is to remember that the strength of an acid and its conjugate base are inverse relationships. As one goes up, the other one goes down. So I'm going to draw three bases here. And I want you to rank them in order of increasing basicity from least basic to most basic. Now, in my opinion, one of the easiest thing to do is, well, let's just make them acids. Let's protonate them and then, rank those acids and reverse it because that's what a the relationship is. If I can rank the acids from weakest to strongest, then I know that the bases go in the opposite order. So let's imagine these protonated. So I'm going to put a proton on those charges. Okay, so these are the acids. You kind of look at them as the conjugate acids to those bases. And I'm going to rank these. So which one would be my strongest acid? Well, the only difference between them is that, a couple of them have halogens and one doesn't. So remember, if we're going to look at REO, the charge is on the same atom. They can all do the same resonance. Now we go to the inductive effect. Notice in A, there is a highly electronegative atom, a chlorine on it. B, there's a somewhat electronegative atom close to the hydrogen. And in C, there isn't any. So this is going to be the strongest acid. This is going to be the weakest acid. So what does that mean for base? It's the opposite trend. The weakest acid will have the strongest conjugate base, and the strongest acid will have the weakest conjugate base. So if I'm going to go from least basic to most, A is the least basic, then B, and then C. Now, the last thing we're going to take a look at is just kind of some, I guess you can call them side effects to acid-base chemistry that we don't really talk about in GChem, but it's important to know for organic chemistry, especially when it comes to doing acid-base reactions. The first thing I want to look at is what's called the leveling effect. And this kind of occurs when you're doing a reaction and you have your reactants dissolved in a particular solvent. If the solvent is amphiprotic, remember that term from GChem? Amphiprotic means it can act as an acid or a base. Amphiprotic solvents limit acid-base strengths. So what do I mean by this? Well, let's say I have sulfuric acid in solution, and I want to deprotonate it with some sort of organic base. If I'm doing this in water, I have to be very careful because that water can also act as a base as well. So I got one base trying to pull off this hydrogen, and I got another base trying to pull off that hydrogen. So the end result is going to look like this. So I got the bisulfate ion there after sulfuric acid is deprotonated. If water acts as a base, it'll make hydronium. And then if the base acts as a base, we'll get this. Now the pKa of sulfuric acid is -9, but the pKa of hydronium is -1.7. That means I'm not going to get the full effect of deprotonating the sulfuric acid because I have something with a lower, I'm sorry, yeah, a smaller pKa value. So really the acid strength of sulfuric acid I'll use the formula here, is not -9, it's going to be -1.7. So what suffice it to say, the reason I bring this up is because we have to be very careful when choosing our solvents for organic reactions, especially if they're acid-base reactions. Most of the time, we want to choose solvents that are not acidic or basic. So something like, for example, a hydrocarbon, like hexane, or an ether, like diethyl ether, because those can't act as an acid or a base. So we're going to get the full extent of whatever acid or base we do want to use. We're not going to limit ourselves or level off the strength of the acid or base that we're using. Now, the last interesting thing I want to look at is how two compounds can be similar in functional group yet have slightly different pKa values. So if we look at these two alcohols, and let's imagine deprotonating this hydrogen, I want you to think for a second, why am I going to deprotonate that one? Those compounds have a lot of hydrogens. I mean, I got like a ton of hydrogens over here, and I got a ton of hydrogens over here. Why am I deprotonating the one in the oxygen? Because that's going to give me the more stable ion that puts the negative charge on the oxygen. And I want to kind of take a little rabbit trail down here. Students at the very beginning of this of mastering this material will ask, well, like, these compounds have a ton of hydrogens on them. How am I supposed to decide which ones I'm gonna, are acidic or not? And this is why we talk about using REO. And eventually you get to the point where you don't have to like go through every single step. You just know that, well, if I have a compound like this, it's got a ton of hydrogens on it, instantly my eyes are going to go to this one because it's one that's on an oxygen. All these other ones on hydrogens. I don't have to worry so much about going through REO for every single hydrogen. Now, if we take a look at the pKa's for these two alcohols, same functional group, deprotonating same hydrogen, there's a difference in pKa's. Ethanol is a little bit more acidic than tert-butanol. Now, again, why is one more acidic than the other? Well, there's got to be something more stable about the anion once it gets deprotonated for ethanol. And what this has to deal with is how much does the solvent help stabilize the ion? In a small alcohol like ethanol, the resulting ion, what we call ethoxide here, can be solvated more. That's just a fancy term by there's more solvent molecules that can surround ethoxide than tert butoxide. So this is solvated less. More solvation means more stability. If that ion's more stable, then the acid it comes from is going to be more acidic. Right? And that's where we're going to end with this unit. I highly encourage you to work through the problem set just to get through to really get down the um, concepts of ranking acids and bases, as well as getting practice with drawing mechanisms. That is something you're going to have to do quite often in organic chemistry, and it will, you know, hurt you every single test, not just this semester, but next semester as well, if you do not know how to draw mechanisms or what the curved arrows mean, or how to properly draw your curved arrows.